Topic 11.3, some spectroscopic identification of organic compounds. You can see there what we're going to be covering, and start kind of with a little bit of review, hopefully, of working out empirical and molecular formula from some percentage composition data. So we're told we've got a certain amount of carbon, hydrogen and oxygen by mass. I've got 40% of that, 6.73 of that, 53.27 of that, and if I pretend that I have 100 grams, that would mean that was 40 grams of that. So 40 divided by 12 is 3.3, that divided by 1, 6.7. I'm being quite lazy with my accuracy here. 53 divided by 16 is also 3.3, which means my ratio is 1 divided by the lowest. This is 1 to 2 to 1. So the empirical formula is CH2O. That empirical formula has a mass of 12, 13, 14, 30. If the actual compound is 90, I need 3 lots of that, so it's going to be C3H6O3. And that's often the starting point for some of these analytical questions that you'll see in this topic. We also need to understand what the index of hydrogen deficiency is, and it's a measure of unsaturation. So how many hydrogen molecules would you need to convert the molecule to a saturated non-cyclic structure? And there are formula out there to work this out, but the easiest way of doing it is probably just by drawing the molecule and thinking how many pi bonds are there in it. So if we take the first example there, that's ethene, looks like that. You can see I've got a pi bond, so my hydrogen deficiency, index of hydrogen deficiency is 1. I could add a molecule of hydrogen to that and make ethane, essentially. Something like ethanol doesn't have any pi bonds, so it's got a 0 there. The last one is chlorobenzene, and you can see there's 1, 2, 3 pi bonds, and so we'd expect it to have an IHD of 3. Right, mass spec, previously used in the course to gain information about isotopes and get relative atomic masses. Well, when the material goes into that mass spectrometer, it fragments, right? It breaks up because it gets bombarded at that starting point by electrons to form those ions. Whilst it's knocking off an electron, it also breaks down, and it can break into quite characteristic fragments. So it's a way of helping us get some information about the structure of more complex organic molecules. And the peak furthest to the right, if we take this example of iodoethane, peak furthest to the right we call the molecular ion peak. Molecular ion peak. So that's the whole thing intact, having lost an electron. Notice that these are all positively charged because that's what this is detecting. Positive ions, they're the ones that get deflected and then detected. So there's my molecular ion. So I know that my substance, let's say I was wanting to verify it was this, is 156, and if I add up all the masses there, it should be 156. Then I can think, well, what am I losing? What could be breaking off? So if I see something at 15 less than that, which I am here, then I'm probably losing a methyl group, and that's the fragment that I'm detecting. Okay, so you can look also what's breaking off via the distances from that molecular ion peak. Infrared is a very useful technique in identifying bonds within a compound, functional groups, let's say, because they will have characteristic stretching or vibrating frequencies. So we tend to look at primarily this section, which is called the band region, and we can use a table of information in our data booklets and look within that band region and see where these peaks lie, or the absorbances lie, and work out based on their position and maybe their intensity, like whether they're big or small, which functional groups are likely to be present in our molecule. So for something like ethanoic acid, we can see that there is a CO in it, and we can also see that there is an OH in it. and we're picking up frequencies as a result of their presence. Now the fingerprint region is specific to a molecule, just like your fingerprints are specific to you. Every single molecule has its own fingerprint, and so if you've got a booklet of data of all these traces, you can check that against what you've got, and by looking at all this intricate, unique information, you can decide what it is. But for most chemists, they will look at the band region and they will see, well, what bonds are we likely to have in here, and compare that with tables of data. Third one we look at is nuclear magnetic resonance spectroscopy, and we look at the proton version of this. So it's all about H's, and what it's going to do is it's going to tell us about the types of H's within our molecule. Probably gives us the most detail of the three, because it also at a higher level tells us what is connected to what. But what we can see is we have, here's our molecule ethanol, and I've got three types of hydrogen in there. There's this one, these two are the same, and those three are the same. And each of those types of hydrogen is referred to as an environment. So on my NMR trace, I expect to see 1, 2, 3 peaks, right? 3 groups of lines, because there are 3 types of H. And in terms of the size of those signals, I would expect them to be, because there's only one here, I'd expect them to be in a ratio of 1 to 2 to 3. Right? So theoretically, if we were to run ethanol, we would see 3 peaks, 3 environments, 3 signals, I should say, 3 signals in a peak size of 1 to 2 to 3. And we have overlying these little squiggles, and these are called integration traces, and they help us easily see the area under the peak, which is representative of the number of hydrogens that make it up. So if we measure the height of that, it's the ratio of those heights would be 1 to 2 to 3. And their position, depending on how the position of these signals varies depending on their proximity to, say, their O group, because they're in slightly different environments, they appear in different places. And in your data booklet, you can look at what's called their chemical shift. Their position on that x-axis will vary depending on what they're next to, as you can see there. All of the samples contain something called tetramethylsilane, which is an internal standard, and that is set as 0. Everything is measured relative to that. Okay.